We're now going to talk about a very important topic in building prediction models, which is validation. The basic idea is this. Um, the goal, when you're building a model, a prediction model of some kind, your goal is not to predict the outcome on the given data. After all, you know exactly what the outcome is, so you don't have to do any prediction at all, or rather, you have an excellent prediction of it. So in fact, what it's really about is you really want to be able to predict the outcome on new, unseen data. So, or for example, you don't want to you might want to build a model, but you really want it to work next week. That's it. That's basically the idea. Okay, now a model that makes reasonable predictions on new, unseen data it's said to generalize well. In other words, it worked well on the data I used to build the model, and now it generalizes to this new data, which it has never seen before. Now, if it fails to make good predictions, you would say that the model is suffering from overfit. Although there are a couple of other reasons why it may perform poorly. Okay, so this is the actual goal. So a very simple way to simulate how the model will really be used in practice is called validation. And so the way that works is it's really very simple. And it looks like this. You're given an initial set of data. And what you do is you remove part of that data. People often just choose, like 20% of the data or something like that, 30%, 10%, and they hold that data, which you really know that data, the values of y, and you put that aside and you kind of hold it in escrow, so it's just sitting there waiting. Then what you do is you build the model or fit the model, and the slang term for that is to train the model on the training data set. That's the data from your data that you did not hold in reserve. The stuff you're holding in reserve is called the test set or validation set. So what you do is you train or fit the model based on your training data. And then what you do is you now do a very good simulation of what you really want the model to do, which is to work well on data it has never seen. And so what you do now is you take the data that you have, but which you did not use to build the model, that's the test data, and you simply try your model on that. And then because you know what the actual outcome is, and you also have a y and you have a y hat, and now we can assess how well we did. So that's the idea. I mean, it's actually a very simple idea. And so you can do several things here. One is you might check the RMS prediction error on the training and test sets. I mean, it would make you feel very confident if they were about the same. You would not expect them to be the same, but you'd expect them to be about the same. Typically, you might expect the test data RMS error to be a little bit worse. Actually, sometimes it's much worse, but okay. The important point here is that it's actually the RMS error on the test data which really matters sort of in practice, right? Now, if this all tests out, you can guess the model will generalize. Now, that's not a guarantee by any means, but it's a good guess, right? So if you go to someone and you say, I'm able to predict demand for this product 1 week ahead, I can get it basically around plus or minus 5%. And then someone would say, well, how do you know that? And the answer would be something like, well, I did it very carefully. I took all the data from the last 2 years. I took I took the first year and a half of that data, and I used that to build my model. And then I took that model and I tried it on the last 6 months of data, when I trained or fit the model parameters, I never saw that data. So that's as if that's actually an honest test because it's actually testing of it. And then you'd say, and there I do about plus minus 7%. And that would be a very happy outcome. And then someone would say to you, well, how about next year? How do you think you're going to do there? The answer is a bit tricky. An honest answer, well, you could say something like this. Well, I would guess or expect to be around plus minus 7%, right? That's reasonable. And they'd say, but can you guarantee it? And the answer is no, you can't. You absolutely cannot. So, okay. I should say that you'll see all of the topics we're going to talk about here from a different point of view and in much more technical detail in a statistics course or machine learning course. But the ideas are all accessible even without those concepts. Okay, so validation is actually super useful because it ends arguments about which model is better, right? So if you have two competing models, and in fact, it's very common for people to produce 50 or 60 different competing models. We'll see a lot of that later. And then the question is, which is better? An example would be, should I fit some data with a polynomial of degree 3 or degree 8? And so the point about that question is it's nothing you can answer by looking at just the training data alone. Absolutely nothing, because the degree 8 polynomial model is going to fit better than the degree 2. Does not mean it's going to fit better on next year's data or whatever, future unseen data. So that's kind of the idea there. You could also have radically different types of models, and you would say, should I use this model, that model? And this would actually, validation would answer that question, right? So, and what you do is, among all your candidate models, you'd use the one that has, the simplest way to say it is the one that has the lowest error, but you might also factor in other things. Like, all other things being equal, you probably want the model to be simple, right? So, for example, if a 10th order polynomial model gave you the slightest improvement in the test error over a cubic, you'd probably choose a cubic, okay? So, as I said, in other courses, you will see this treated in more detail and things like that, more formally. Okay, so let's look at an example. So there's 100 data points, actually 200. 100 of them are the training set, and we use that to fit a quadratic, a degree 6 polynomial, a degree 10, and a degree 15 polynomial. Now, what's showing here is another set of 100 data points, which is the test data point. And actually, just if you run your eyeball over it, looks pretty good. This is, and it's honest, right? That here, that blue curve is making a prediction on data it has never seen before. So it's an honest simulation of what you want a prediction model to do. Okay, this is sort of a typical, this is a typical situation. So here, for example, I have an increasing degree in my model. Now, by the way, a model of degree 10 is also a model of degree 15, because the last 5 coefficients, you just make them 0. What that tells you is that as the degree increases, your training error just goes down. It gets better and better because, it could also stay the constant, right? Because the point there is, if I can fit something with a 10th degree polynomial, I can't fit it worse with a 15 degree polynomial. I can only do better. Okay, so the blue curve here shows you the training error, and sure enough, it just goes down. Now, a lot of times common sense tells you that what you're looking for is it's the traditional knee of the curve. Knee of the curve means something around right here, where the marginal improvement is not good. Okay, so but validation makes this pretty clear. So the red shows you the performance of the model on data it has not seen, okay? And let's see what that looks like. Well, for order 0th, that's a constant model, by the way, 1, 2, 3, 4. It's pretty close. And what you see, though, is very interesting. The 7th degree model is actually worse on the test data than the 6th degree. So now that's not something you could guess or know. You just simply have to try this with the data to see that. And it's pretty simple. You can understand why. And out here, it's like considerably worse, right? So that here, if I fit with a 20 degree polynomial, I have an RMS error of 0.21, right, on the training set. And yet on the test set, I'm almost double that at 0.4, right? So the old school rule of thumb might be to say, it's degree 6 that has the lowest test error. But honestly, degree 4 looks pretty good to me too. And the reason is it's not a whole lot. It's not a whole lot worse than that, and it's a simpler model. So, okay, so this is the idea. These are very important things. You're going to see this in other classes, or you may already have seen it in other classes, but you will see this in other classes. Let's just leave it that way. Okay, now validation, also called out-of-sample validation, right? There are many variations and extensions on it. And I'll just mention one other one, and this is another one, probably the second most widely used. It might even be the most widely used, called cross-validation. And it goes like this. I mean, so this is how it works is what you do is you take your original data and you divide it into 10 groups. By the way, very often this is done randomly. So you randomly take your data and assign them to 10 different groups. Then what you do is the following. And these are called folds of data. What you do is for I equals 1 to 10, you fit a model using all the folds except the ith one. Okay, and then you test that model on the ith fold. And so this is an honest test in the sense that you are building a model based on some data, and then you are evaluating on data it has never seen, which is, after all, what we want a model to do. So here you get 10 different honest tests of your model. Honest test means you are trying it on data it has never seen. Okay, so this is very common. Five-fold means you do this and you chop it into 5 parts. Tenfold, and by the way, there's lots of other methods, but these are kind of the ones you might hear about the most. Now, it's actually also very good sort of engineering, because you get to do some common sense checks. So you get to see what you do is you look at the test RMS errors, and if they're much bigger than the trained RMS errors, that's a red flag. The other thing is you can look and see if the test and train RMS errors are consistent. Then that allows you to guess with considerable confidence that it's going to work, that model is going to work similarly in the future. It's not a guarantee. So I remember once in class I asked somebody. I remember asking. I said someone like, "Oh, but that would never happen, right? I mean, once you do cross validation, your model's going to work, right?" And there was silence, and then somebody raised their hand and said, "No, that could happen. You could do full cross validation, and then all of a sudden your model could work very poorly." And I would say, "Well, what would you do when the CEO comes into your office and pounds the desk and says, do you realize what the consequences of this are, blah, blah, blah?" And the student looked up and the CEO screamed and says, "What happened?" And then the student just looked at me and said, "Things changed." So that's simple, right? So if you're making a model of for advertising or demand of a product or anything involving kind of people and social systems and economic systems, of course they can change, right? Newtonian mechanics, by the way, doesn't change that often, but okay, another story. Let's look at an example and just see how this works. So this is a super simple example, right? But nevertheless, it's going to show you how this works. So this is this really dumb thing where we are going to predict a house price in thousands of dollars based on a mere 2 features, which are the area in thousands of square feet and the number of bedrooms, okay? And we took 774 houses. This is in some place, I forget where, over some time period, not expanding, like 10, not covering tens of years, but, maybe a year or something like that. And that was divided into 5 folds of 155 sales each, completely just at random. Okay, then let's look at what we did. So in the first one, we removed fold 1. That's 155 house sales. We removed it, built it on the remaining, 774 minus 155, so 620 odd, about 620 things. That's how we fit our parameters, of which we have 3. By the way, we have the offset, we have beta 1 and beta 2. These are very, very elementary, simple models, right? Okay, and here are the results. These are my 3 parameters. That's my training test, and that's my test. That is my training RMS error, and that's my test RMS error. This is exactly what you'd expect. You'd say, whoa, it's 74, and then on the test, you don't expect it to be as good as the train or whatever, but same ballpark. So You see 74 and 78 and you go, yep, that's good. But if someone says, look, before we put this model into production, I really need to be more confident than just this, right? Okay. So then what you do is in fold 2, we remove a different 155 ones. We remove fold 2, fit the model, and here's what we get. And what's kind of cool is the parameters are not the same, but they're kind of in the same ballpark, which is also a good sign. Here, the training RMS error is 75, which is like, okay, by the way, if these were exactly the same, you'd be suspicious, right? You'd say, it doesn't look right. And here, this is interesting. Look at that. On the test RMS error on this second model is actually better than the training one. And can that happen? And the answer is sure. And if someone says, how did that happen? I think the answer would be luck, right? So basically what happened was you fit a model, you applied it you used it to predict the prices of houses in fold 2, and for whatever reason, that was a set of 155 houses that where our model was reasonably good at making the guesses, and so we actually did a little bit better. And look at the, so you go on and you kind of get the idea. Actually, the test set did better a bunch of times. Usually this is because there's some hard to fit houses. And maybe if they land in the training set, that's cool. And if your test set is more benign, you do well. But this gives the idea, and this gives a whole lot of confidence in this model, right? And so based on this, you would say, by the way, based on this, you could go back and refit based on all the data, right? Or you could just choose any of these. I mean, it wouldn't matter. But the point is that the offset should be on the order of, I don't know, 55. I mean, I'm just making that up, right? Something like that. Beta 1 clearly should be on the order of, I don't know, 150. Beta 2 is like, I don't know, minus 19. I'm just making this up, right? And we could expect a test error that is somewhere in the range of, 70 to high 80s. And perfectly reasonable. We would not be shocked with any of those numbers if we use this model to predict housing prices, other house prices. This would be sort of our confidence. Okay, so this is just an example of 5-fold cross-validation. The last topic we're going to talk about very briefly is the so-called feature engineering. It's a way to interpret those basis functions that we talked about earlier when we started. And it's also a very important thing in fitting prediction models is so-called feature engineering. I'll show you what that is. This is just a hint of what feature engineering is. As you will see this in other classes, internships, whatever. You're going to see this. So, but this is not a bad time to sort of explain the basic idea. Okay, so basic idea is this: you'll start with some original or base feature X, right? That's the actual like raw data that you have, right? Then. Well, as this whole chapter started, the key was to choose these basis functions. And one way to think of them is that they are mapped or it's a transformation on the original stuff. And maybe sometimes the transformation is very minimal. For example, in a regression model, pure regression model, the transformation is we take your original X and we add a new feature, which is 1 in front of it. So that's very benign. But it can also get real weird and crazy, what you do in these mappings, right? Once you've chosen these, what you do is, of course, you fit a model this way. And then, of course, and this is always the case, you check the model using validation, period. No one wants to hear, if you'd say, how's your model? You'd say, oh, awesome, I have this RMS error. And they say, so basically, it would be expected you would report to another person the test RMS error, or out of sample RMS error, or cross-validated RMS error, something like that, right? Certainly not the training, because no one cares about the training error, basically. Okay, so I'll just mention a couple of things that people do to transform features. One, and this is very common. Again, this is not central to this course. This is just that we've arrived at a point where you can actually do some like pretty cool stuff. I mean, like actually very powerful, very cool stuff. One is called standardizing. And that does nothing but take your original features and then it offsets it and scales it. The idea being that you would like your features to kind of have a range from -1 to +1. I mean, roughly, right? So that is actually maybe almost universally done in when you're using these types of models, right? Is you would do that. And these new standardized features are called, I mean, they're approximately standardized. They're called z-scores, not surprisingly, right? And now they're completely interpretable, right? So if z3 equals 0.2, it means that the third feature is a little bit above the mean. That's what it means. If it's -2.5, it's surprisingly below the mean, like a kind of a 1 in 100 kind of thing below the mean. That's all. Okay. Here's another trick. If xi is non-negative and spans a wide range, you replace it with a log of 1 plus xi. So I'll give you a couple of examples of this. Well, here's one. Well, actually, we could start with, here's one. Things like this. Often counts, like the count of how many people listened to a song or how many people bought a product. Some products have sales measured in like, 5, 10, right? Others, you've moved like, 350,000 or something like that. And so these, when the xi's span this huge range like that, it's very common to take a log or log 1 plus x to just get the scale right. So that's extremely common in this, and that's just a log transform. You can create new features by as functions of the existing features. Now we've already seen that because that's one way to think of what a polynomial thing does, right? In a polynomial, when we do polynomial fit, the raw feature is a scalar. It's a number. Then you can think of it, we transform it, right? F1 gives you 1, F2 gives you x, F3 gives you x squared. That's like a transform, and x cubed, and so on. So that's how you think of a polynomial model. But you can do other cool ones. Like here's one: is you take here I'm taking the first raw feature, I subtract b, and I take the max of that and 0, and so I get a kind of a cool thing. So here's b. And so it just simply looks like this, right? It's the max. It's this function here. It goes there, and then there, right? And so this new feature, if x1 is less than b, is just 0, right? Above b, it gives you the amount by which it's above b, and that's a you call that the high feature, right? By the way, this is useful to do in conjunction with standardization. So if you do standardization, a good number for b might be 1 or 1.5. And you'd say that's a feature which is almost always 0. But basically what it does is it tells you the amount by which b is the original feature is really large. And you can do the same thing with min. I won't talk about that. So now we'll do an example. And we're going to predict house prices. And it's a this is a very simple thing, but I'll start with the raw the base features. So the base features we have 4. I should say that when people actually predict house prices, it's not based on 4 raw features. It's based on hundreds and hundreds, right? Just tons of stuff, right? So these are highly simplified, but at least this model will not be as extremely simple as the other one, where we were predicting it based on the house area, and the number of bedrooms. So here it is. X1 is the area of the house in 1,000 square feet. X2 is the number of bedrooms. X3 is what people would call a Boolean feature. So it's either got the value 1, means that that's a condo, actually, a condominium. 0 means it's a house. X4 is the zip code. Now that's interesting, right? So it's a 5-digit integer. It's a zip code, and there are 62 different zip codes. Okay, so X4 is, again, you don't need to know this, but it's what you call a categorical feature, meaning it only takes a finite number of values, in this case 62 different zip codes. Okay, so we'll use 8 basis functions. I'll say a little bit about how do you do this. Oh, by the way, the act of taking raw features and coming up with these feature mappings or basis functions, fi, it's called feature engineering, and it's probably one of the it's like in some sense that's sort of the essence of building models. Okay, so we'll use f1 of x equals 1. That's a constant. That's an offset feature. F2 is x1. which I believe is just the area of the house. F3 is interesting. It's the max of x1 minus 1.5 and 0. So F3 is a feature that is the number of 1,000 square feet by which your house area exceeds 1,500 square feet. That's what X3 is. So X1, that is indeed what X3 is. Sorry, yes, the F3 of X is that. The transform feature is, I guess we called it X tilde 3. Anyway, whatever it is. So it tells you that. So it's 0 for small houses, and for big houses it might be big. Okay. F4 is simply going to be the number of bedrooms. F5 is going to, so these are very simple encodings or feature mappings or engineering, right? So I'll just use the Boolean as it is. F6, 7, and 8, they're Boolean, so they're either 0 or 1. And what they're going to do is they're encode 4 groups of zip codes. So in other words, we take the 62 values of zip codes, we divide that into 4 like neighborhoods, and then what will happen is each of these will be 0 or 1, and that'll encode which neighborhood you live in. Okay, we do 5-fold model validation, and here are the results. So we have 8 parameters in this model. It's slightly, it's a bit more complicated, and here are so the first thing you do is pretty cool. The first thing we should do is look at this table here. So you scan down the train thing, and you get different training RMS errors, so like 67, up to 70, and that's good. Okay, and you look at the test. The cool thing is that the test it's not hideously off from the train. It's in the same ballpark. A little bit bigger, for sure, a little bit bigger, right? Like, look at that guy right there. Of course, here's a time when you were super lucky. But the point is, it's in the same ballpark. And so I think what this would tell you is that this model, I could refit the model on all the data, and I could make a pretty good guess that for houses you have never analyzed, you're going to get it probably with around an RMS error of about 70, whatever it is, around on the order of 70. Okay, so that's what this shows. You can also look at the coefficients, and what you see is actually kind of encouraging. It basically says that the coefficients are what people call stable. In other words, that looking at different folds of the data, you don't get exactly the same parameters, of course, but they're kind of stable. Like you just take a look at this one, and you'd say, well, okay, that's there's no true value of theta 7. That's ridiculous, right? But the point is, this says that we consistently assign a value of around, I don't know, minus 109 or 8 or something like that to theta 7. Okay, so this is the basic idea, and this would show you how you might do it in some real setting. Now, in a real setting, it'd probably be much more complicated, and you wouldn't have 8 parameters. You could easily have 800 or 8,000 parameters. One last thing is you could reasonably ask, like, how did you come up with this? Like, and here I'm just going to tell you the truth by fiddling around. Okay, so that's how it was done. You try a couple things. Oh, very important point about that, which is a part that we do not apologize for, and that's this. You might try 50, 100 different weird candidates. Like, for example, over here, why 1.5? Why not 1? Why not 0.5? Why not 2? So the way you do that is you just try it. You build it, and then you do 5-fold cross-validation. And you see which of your 50 different attempted models has the best 5-fold test error, or simply the best test error out of sample. And that's your candidate. So in this sense, you let the data tell you which model is the right one. Right? And by the way, if it's not a whole lot better than a much simpler model, you kind of go with the simpler model, right? So I didn't mention that, but I do want to mention that about now. Here you can see that we're getting test errors in the 58 to 70 range. It's fine, right? But let's go back and look at our really simple model over here. Here you go. And here's what you see. These numbers are definitely larger, period, right? So our other conclusion from this analysis is that all of this feature engineering that we did here actually did something. We came up with a better model. So now, whether or not this is sufficiently better to justify this crazy model, it's another story. And I guess that story depends on what you're going to do, right? In some applications, it's important that the model be simple because you have to explain it to somebody. For example, possibly a regulator or somebody like that who needs to know what are you doing and how are you doing this. Or to take another example, it could just be like some crazy hedge fund where I couldn't care. You couldn't care in the slightest what the model means. What you're interested in is, does it make good predictions of the way prices are going to move? And if it does, we'll use the model, and we don't care what it means. So there are lots of variations on that.